Okay, 4.1, here we go. It's on maximum and minimum values. We've talked a little bit about this already, so it shouldn't be totally new. Okay, here we go. Definition, enough talking, we're starting. Let C be a number in the domain D. Yes, of a function f. So what kind of value is C? No, well yes, but what kind? It's an x value. So C is a number in the domain D of a function. Then f of C, what kind of value is f of C? Is the absolute max of f on the domain if f of C is greater than or equal to f of x for all x in D. We have talked about this before. It's basically, is there a highest y value? If there is, that's the maximum. During what? Yeah, yes. Okay, it's an absolute minimum. If f of C is less than or equal to f of x for all x in D. On D. If f of C is less than or equal to f of x. So again, is there a lowest y value? If there is a lowest y value, it doesn't matter how many times the function attains that lowest y value. If there is one, then that's the absolute minimum. Because let C be a number in the domain. What kind of values are in the domain? Right. Okay. Relative max of f if f of C is greater than or equal to f of x for x near C. So the difference in the absolute max and the relative max is that the absolute max has to be true for all x. For every member of the domain, that has to be the highest y value. For the relative max, it's saying that only where x is near C. And we'll draw examples in a second. Let's go ahead and write relative minimum first. And relative minimum is the same thing, just less than. That's that good. If I did.
Were you like all right at it, or were you going
All right.
Okay, so I still have to
Absolutely.
You supposed to be calculus teachers? I could not.
Okay. Let's draw some pictures. So
You're actually a superhero. I could not do this.
teach you people? I know.
Yeah. Teach us
On video.
period. Add calculus to that.
Okay.
Holy cow, that's in the video.
Okay, so here, do we have an absolute maximum value? Yes, we do. It's whatever this y value is. Do we have a relative maximum value? Yeah. It just says that it has to be the highest y value for some x near C. Now, if this is C, just pick somewhere near. We pick these x values. This is still the highest y value in that little interval. Sure, and actually this one doesn't matter what interval you pick, it'll still be the highest one because it's the absolute max. Okay, we could have something like this. Is this an absolute max? No. Is it the highest y value? Is there one? No, there is no highest y value, so this one does not have an absolute max. Does it have a relative max? Sure. See, for some x near C, if this is C, then there's some x value where it's the highest thing. Now, if you get too far away, what's going to happen? It's not going to be the highest y value, but that's what it says near C. Because near C could mean different things in different problems. As long as there's some open interval that you can pick that has a highest y value, then you're good. Got it? Okay, we also talked about this on one of the previous tests. What if I have this function like y equals 2? Does it have an absolute max? Does it have a highest y value? The highest y value is 1. 2. The highest, okay, back up, rewind. Okay, the highest y value is 2, right? Does it have a highest 1? Yes. By default, but yes. It is an absolute and a relative max. So we are kind of getting the idea between absolute and relative, right? Okay, something else is global. So, and I'll use those words sometimes. When we talk about a local maximum minimum, that's like a relative, locally a maximum min, and we talk about globally, so over the whole function. So if you hear those words, local, global, they go with relative and absolute. Okay, great. Extreme value theorem. Being continuous, f being continuous on AB implies that f has an absolute max and an absolute min. So if we're talking about a closed interval, this extreme value theorem tells us that there is a maximum and a minimum on any closed interval. And why is that true? Then I'll say it at once. You weren't listening. Alright, and if you have a closed interval, why does there have to be an absolute max and an absolute min on the interval?
Because you have space to work with, so you know the point where there's no
Okay, so take this one. Take this one in the middle. This one didn't have an absolute max or an absolute min, right? What happens if you take a closed interval? So let's say this is my interval and this right here. Why does there automatically have to be a lowest or highest point?
Because you know the highest point, you know the lowest point.
It just is there. Okay, so the idea is that it changes from having to be a maximum that looks like this and a minimum that looks like this. That's not necessarily true anymore, right? We're looking for what is the highest y value, and there is one. Now, it could happen at the places where we have extrema, or it could happen at the endpoints, right? That's what changes. It could happen where you have an actual, what we usually call a max or a min, or at the endpoints is the only place. Draw a picture. And then what? Okay, this is not a function. It's fine. It's fine. Okay, it's fine. Yes.
Okay, what is the slider?
Right. It's either gonna happen somewhere that you usually think a max or a minimum would happen, or it's going to be really close.
Carol, tell that where one would normally happen. Where one would normally happen. Or if it didn't do that, or if it was still that.
Right. Okay. Great. So we have the extreme value theorem. There has to be an absolute max or an absolute minimum on the interval. Okay. One last theorem. Fermat's theorem. Fermat. If f has a local max or min, hush! Y'all have done nothing but talk the whole time. Be quiet. If f has a local max or minimum, that it implies, sorry, I'm writing the wrong thing. If f has a local max or min at x equals c, and if the derivative exists, then f prime of c is equal to 0. If f has a local max or min and the derivative exists, then the derivative has to be 0. If you think about a maximum, if you draw a maximum, the derivative is 0 there, right? Okay, a couple of things that I want you to be careful about. Is everyone done writing this? Yes. Sorry, I know. Okay, a couple of things. Be careful that this is not saying. It is not saying that f prime of c equaling 0 implies that there's a local max or min. So some students think that, oh, that means that if the derivative is 0, there has to be max or min. That's not true. And the function that ruins it is y equals x cubed. What's the derivative at 0? 0. Is it a maximum or a minimum? No. So just because the derivative equals 0 doesn't mean that there's a local max or min. The other thing that this doesn't say is that if f has a local max or min, then that implies that the derivative is 0. And the counterexample to this would be something maybe like absolute value of x. So absolute value of x has a minimum value. But what is the derivative there? Huh? Undefined. Absolute value of x has a minimum value. But the derivative is not 0. The derivative is undefined. So if you go back to the theorem, it says if f has a local max or min, and if the derivative exists, then the derivative is 0. So two conditions. You can't just take one, you have to have both. So what it does say is that if f has a local max or min, then the derivative has to be 0 or undefined. And that's actually the contrapositive of the statement. Y'all remember that from geometry? So f has a local max or min implies that the derivative is either going to be 0 or it's going to be does not exist. Okay, your homework for tonight is going to be what's on the grid.
Good morning. dress wear uniforms to the front office. And at this time, group 1 may begin moving to the arena.
Homework is the grid for today and the handout number 9, the handout on related rates. Whatever's on the grid for today.